Piers asked me to talk about the modeling Wayback Machine. We've talked a lot about scaling from molecules to the orbit in Joe's talk and so on. I always thought of Fife as scaling from chiggers to C-130s. And most of my memories associated with Fife revolve around dusting my ankles with sulfur and scratching my way back. So it's odd that Piers asked me to talk about modeling because I spent most of my time grubbing around in the field. But remember what modeling was like back then. This is the kind of computer that I lugged out to Fife, and this is how we communicated with each other with that funny thing there on the right. That's a telephone. You can't put it in your pocket because it's attached to the wall. And it connected to that thing there that could hold, the equivalent of 15 or 20 minutes of eddy covariance data before you had to change disks. I was at NASA Ames for most of Fife, which people don't remember. I'm at JPL now. This is my second NASA tour of duty. But back then, we all knew that you could not scale from leaf to canopy. The state of the art were these individual-based forest models that were based on growth curves that were calculated from the geographic range of tree species. Hank Sugar told us that you couldn't scale from the leaf to canopy. He asserted it many times. That talk had a huge impact on me. But the state of the art were these individual-based models in which trees competed with each other for light. The curves were based on the northern and southern range of the species, locked down onto temperature and rainfall maps. And we had no time steps smaller than a year of primary productivity with which to calculate carbon fluxes. And so we had no fluxes in our model. We had delta biomass over periods of years. There were at least two big reasons that Fife addressed why we couldn't scale from the leaf to canopy. First, canopies were complicated. They still are complicated, and we didn't have simple scaling rules. And second, even if we had scaling rules, we didn't know the answer. We had no way of measuring photosynthesis at large scales, and we had no way of measuring respiration at large scales. And NPP, which we could measure, delta biomass, was the relatively small difference between those two big fluxes. We really had no idea what the right answer to those fluxes was, except at rather small scales from chambers that you could put down over short grasses. Piers, it is probably not widely remembered, had the world's biggest chamber, which required a crew of husky field assistants to lug around. They would rush out, put it down, make a measurement before it got so hot that everything in it died, then they would take it off. But that was the sort of information that we had about carbon fluxes. You could measure a carbon flux on a time scale in between when a grass got started out photosynthesizing and before it got too hot and died. So we didn't know the answer. So we had models. John Norman in particular had a very sophisticated model, but we had no way of verifying whether those models gave a good answer at scales larger than the centimeter or so of tissue that you could put into a leaf chamber, which was also, by the way, quite new at the time. But these were heady times for modeling. As Joe Berry pointed out, the Farquhar model for photosynthesis was very much on everybody's minds. It's one of the reasons why people wanted to scale from the leaf to the canopy. And in my neck of the woods, we were also beginning to understand heterotrophic respiration and how the carbon storage term worked. And this is a reasonably contemporary figure of the century soil organic matter model, the representation of photosynthesis on the left-hand side. And these papers are beyond seminal, right? So the Farquhar paper now has over 5,000 citations. It's one of the 10 most cited papers in geophysics. The Century paper that describes the soil parameterization has over 3,000 citations. It's one of the 15 most cited papers in geophysics. And so this was an area of enormous ferment. And by the way, these papers continue to be cited at rates higher than most contemporary papers. So empirical evaluation at the Kanza. I'm going to talk about something that's a little different. Ray made this point that even simple ecosystems aren't simple. At the Kanza, we had an early meeting where I remember peers getting up and talking about grasslands and their characteristics, one of which was that they were flat. I had done some of my PhD work at the Kanza, and I knew that it was not flat, and that in fact the landscape was quite significant. Ray pointed out that these gullies with woody vegetation are very important to the landscape. That's a whole nother talk, an area that Jeff Dozier and Frank Davis and I worked on. These gullies that cover 10% of the landscape contribute about 30 or 40% of the flux. And in the work that my group did, we used the landscape because there were differences in photosynthesis and productivity of well over 100% between the ridge tops, which had shallow soil and behaved as if they were almost arid ecosystems, and the lower slopes, which received quite a bit more moisture, had deeper soils, and behaved as if they were what we might think of as tall grass prairie. I also just want to point out that I believe a human with a drafting table, if anyone remembers what those are, made this figure with a pen. It was then photographed. And this is from the original journal article. Remember that when you go back to these papers from the early 90s, they are scans made from pieces of paper. And so I'm going to show some of these figures. I actually coded this up and replotted a bunch and decided to use the original figures. So these were really done by my colleague Tim Cattell based on the transects that we measured. If you look at these figures, these are actually kriged using a software package available in the late 1980s. And it shows the trends on the upper part, biomass, and on the lower part, leaf area index. The axis into the screen is day of year. The other axis is distance along the transect. And so you can see that there's both spatial and temporal variability reflecting both time of year, but also differences in the seasonality between these wet and dry sites within the landscape. And these translated into gradients in both the amount of nitrogen and the maximum velocity of photosynthesis with time and across these gradients. We were able to make good use of this to look for a scaling rule that related growth, photosynthesis, and light interception. And it turns out that there was a gradient basically in these systems between the nitrogen-limited low light interception systems. So these were parts of the ecosystem where the soils were shallow and infertile, where there was little enough growth that the systems produced relatively little biomass. This doesn't really work. So the left-hand side, nitrogen limited. The right-hand side, light limited. These are parts of the ecosystem where you have abundant growth, where you have sufficient foliage produced that essentially you intercept all of the incoming radiation. And this gradient in light interception had really dramatic effects on the way the plants responded. So that when you looked at the height distribution of photosynthetic capacity, it fell off with the light response curve quite dramatically, going from the fully sunlit upper canopy to the deeply shaded lower canopy. And in the lower productivity systems, you could see that the gradient in photosynthetic capacity, where you're going from middle button, where you're going from
The screen doesn't.
No, the light comes on and yeah, you just can't see it. Screen doesn't reflect well enough. So you can see that the gradient was reduced. And this led eventually, so you can see it in the light response curves too. So on the low biomass parts of the ecosystem, you could see that the light response of the upper and lower canopies were virtually identical. Whereas in the very productive parts of the ecosystem, the light responses in the upper part of the canopy and the lower part of the canopy were dramatically different. And it turns out that this was captured in the, is this 92, Joe, 93, SIB2 paper, basically by arguing that the photosynthetic capacity should scale with the time mean light availability at each height in the canopy. This leads to a really simple scaling rule for integrating over canopies that's been highly successful for many years. There are exceptions to this rule, which was, I think, first proposed based on laboratory studies by Chris Field in the late 1970s. But it worked beautifully to characterize the spatial variability and the vertical structure of canopies. And it allowed essentially collapsing the complexity that we used to argue prevented us from scaling from leaf to canopy, allowed us really to condense that into almost a zero-dimensional representation. It also implicitly linked light interception, photosynthesis, and nutrient availability in ways that I would argue we still do not fully understand. So we had a scaling rule emerging from Fife, but now what's the answer? Because the scaling rule still doesn't tell you what the answer is. That is to say, when you add up all of this elegantly exponentially decaying flux through the canopy, what's the actual flux per unit time on relatively short time scales? Again, at the Kanza, as you recall, we had these seasonal biomass measurements. They told us what the net primary productivity was. But it was really eddy covariance, really deployed for ecological timescales for the first time during Fife, that gave us the answer. And just a few reminders that Fife eddy covariance data provided the first flux data from a major field campaign. Really the first operational deployments of multiple systems so that they could be intercompared to aircraft to evaluate their regional representativeness, but also intercompared with each other so that the technique, which remember was then really in its infancy, that the technique could be established in terms of a quantitative benchmark. And I want to make the point that Ray and others have made too, which is that Fife data have been used to benchmark essentially every land surface model ever since. If you look at the citation history that Forrest showed, many papers are still using the Fife data as the first benchmark for evaluating either new land surface schemes or updates to existing land surface schemes. This is just a random example that I picked. This is one of Bob Dickinson's group's papers. Again, this is from 2002. These data are still being used day in, day out by modeling groups as their first check on whether changes or updates to models generate more or less the right answer. And from a modeling point of view, the deep theoretical insights that linked plant allocation of resource, light harvesting, and photosynthesis to the quantitative flux that those scaling rules produce in the atmosphere are fundamental to our ability to model land surface atmosphere exchange, but equally fundamental to our ability to model the carbon cycle, its variation on diurnal to interannual timescales. So work at the Kanza established linkages between the biophysical and the biogeochemical that in fact are still being fully absorbed into models. Integrating VC max as a prognostic quantity rather than as simply an assigned variable from a lookup table is still actually in its infancy. We still don't fully understand nutrient limitation. or the links between the biogeochemical and the physical controls. Does nutrient limitation equilibrate to energy availability, as we argued in our late 1970s papers, or does the geochemical evolution of nutrient availability control energy harvesting, as Peter Vitusek and his colleagues have argued? Clearly, those are both true on different timescales. So scaling from canopy, now routine. It's the standard for modeling. Models that don't use a representation of photosynthesis are now almost unheard of, except in some areas of applied science. But individual-based models are coming back. That is, having addressed many of the issues associated with the diurnal to interannual variation in photosynthesis, we're now seeing the role of mortality and recruitment of trees becoming significant again as we again begin to tackle simulation and trying to understand things on longer timescales. I think that Forrest pointed out very effectively that the remote sensing of biomass using active radar and LiDAR remote sensing techniques is giving us the remote sensing ability to go from the time scale of photosynthesis to the time scale of forest disturbance and recovery. So there are a few lessons learned. Actually, my first slide with the title Lessons Learned had 30 or 40 points on it. And this is actually just kind of an arbitrary subset of that list. I want to start at the bottom and point out that these field campaigns, as Piers said, are addictively fun. When I look around this room, I see a lot of gray hair that was not gray on the first field campaign that in fact, in some cases, I see no hair. We're all still doing this. So clearly, the intellectual and visceral excitement and payoff from these campaigns is enough to keep people in this business for a long time. And I want to argue that some of that is intellectual, some of it isn't. Some of it's just plain adrenaline. And I think that Forrest captured some of that with these daily planners. There's just a lot of intensity to it. But Fife, Boreas, and LBA catalyzed an interaction between atmospheric and ecosystem science that has come to define much of NASA's program over the years. It's made a huge contribution to the intellectual development of Earth system science by bringing people together across disciplines and by bringing observationalists, modelers, theoreticians, and technologists together. And the impact of that on science, I think, can really not be overstated. And I think that over the course of the morning and the rest of this meeting, you'll see many of the unexpected ways in which this synergism, you know, a bunch of people going to a very small place in a very seemingly simple part of the United States has had implications to the global weather forecast, to our theoretical understanding of how plants work. And it established this precedent of a close partnership between modelers and observationalists that I think has been just enormously fruitful. And I just want to wind up by saying that there are still an enormous number of open questions hidden in plain sight in the Boreas and Fife data and in the LBA data. And you can see that in that people are continuing to publish on these data sets to this day. And not just to evaluate models in a relatively routine way. There are still new discoveries being mined from these data. And I think that they will continue to be for many years. It appears that the publication half-life of these field campaigns is something like 15 to 30 years. Most of them have not yet stabilized. And so the resource that's created by these projects is just of incredible scientific value. So I want to wrap up there and not stand between people and their sandwich.